Alright, so this talk is not a live coding talk. It will have code in it, and it will have a lot of code in it, because I love talks with a lot of code in them. I think there's places at conferences for talks of all types, but I like the ones with lots of code. I was going to do this as a live coding talk. I've been warned thousands of times about how live coding is horrible. Never do it, angering the demo gods and all. I didn't listen to those people, so I submitted this as a live coding talk. But luckily, it had to fit into 40 minutes. I did preview versions of this talk in a few user groups, and they weren't time-boxed. The first time I gave a version of it, it took me 80 minutes to live code it. So I thought, okay, this isn't going to fit. So thankfully, there's plenty of time at that point to rework it. So I reworked it a lot, and I gave it another user group. And so this time it took 80 minutes. So finally, I had this huge insight into how I could reduce the time substantially. I just stopped test driving it altogether. So I put a lot of effort into doing that. I reworked it, changed it a ton. It took 80 minutes. So since Jim and everyone after me today would murder me if I took 80 minutes, we're changing it a bit more drastically. So no live coding, but we're going to walk through the build iteratively. So it's a repo up on GitHub, and we're just going to walk through the commits in the order that sort of they happen. Since I've mentioned murder, I figured here's a cat, and now nobody has to remember the violence talk. Anyway, I've got a ton of code every slice to get through, so no long cat pauses. All right, so ElixirConf, I guess, just wrapped up or is going on. And the big new feature is essentially a crappier version of Phoenix channels called Action Cable. We're using Phoenix channels for this project because they're awesome. I love Rails. I still write APIs in it often, but there's no way I build this sort of thing in Ruby. I've done multi-threading things in Ruby before, and I don't want to do them anymore. So Phoenix, though, is really, really nice for building WebSocket-based apps in. It also saves me from having to build all kinds of things in Node.js, and that's great because JavaScript is gross. So before we kick off the actual talk, a few links. So first off, I mentioned all this code is up on GitHub, and all these commits are there in order. This talk really is just walking through that repo. Next, I do this Elixir Sips thing. I record videos of myself learning about Elixir. That's been going on for about a year and a half, and people pay me for access to them. And if that sounds appealing to you, awesome. And then finally, I'm the CTO of Isotope 11. We're a software consultancy, and we'd love to help you with projects if you need help with them. And so now I've plugged my company, and I've justified us sending me out here. So let's get on to the code. And do just yell at me or something if I'm moving too quickly. I have a tendency to talk fast even when I'm not presenting, so I won't be offended. Anyway, the first step on our journey is just we build a basic new Phoenix application. The only modifications we made to the bog standard Phoenix new is we modified page index to be a single canvas element, and we modified the app.js. So remember how I said JavaScript was gross? Good, because there's a non-trivial amount of it in the talk. Here's some of it. So here we're just getting a 2D context to the canvas. This is readable, right? I got the font size good? Awesome. Okay, so here we're just getting a 2D context on the canvas, and then we're building an object called app that we have a few functions on. So we built a function called run Tetris, and it just kind of sets up this fake state and then draws a board, which right now it doesn't actually draw a board, right? It logs a piece of text at the console. So far this is not rocket surgery, but it gives us some kind of framework to work with. The biggest thing to grok here is, as Chris mentioned, we have ES6 by default, and so this is the first time outside of like an Ember application that I've used ES6, and it was really enjoyable. So we're going to look at the application as we go through it, so bear with me. This is... All right, so one second. This is the part I should have finished before. Oops. Okay, so if we look at the console, yeah, we're drawing stuff. So we start our application, and we're good. Moving on. Okay, so now we actually want to actually do something like actually draw and not just write some text at the console. So let's do that. So here we've mocked out what our game will look like from the JavaScript side. There are only two components as far as the JavaScript renderer is concerned. There's the current board, and there's whatever the next piece is. So you can imagine our backend continually updating the data structure and then the client rendering it. So that's almost all that the client has to do. If you look at the board, you can see it consists of a bunch of zeros that represent empty spaces and a 1 to represent the component of the L piece, right? So there's an L and you can see it's ones. So can you imagine how boring this would have been to watch me type live? Okay, so next we pass the drawing context and state into a draw function. So this function just draws the board and it draws the next piece. There we go. That's easy enough to see. Drawing the board consists of drawing a frame around the board and then just drawing the board as like an array of pixels. Only they're not really pixels, right? They're these bigger blocks, starting at coordinate 0, 0. So here you can see draw pixel array. This is just loops over this sort of two-dimensional array, finds whatever's inside that position. And then if it's a 0, it doesn't do anything. And otherwise, it draws, based on the number, it draws a square. So like a 1 is like yellow. Anyway, drawing the frame just consists of drawing some lines around the boundaries of the board in our game structure. And yeah, I mean, that's not that exciting. It's another couple of for statements, right? This is not very hard. And finally, we can see what draw square does. So it's passed a context, a coordinate pair, and a brush. And it kind of blows those things up into 25 pixel squares. And then it draws them on the canvas using whatever brush you passed in. And the brush is just a RGB value string. And so you can see that this brush for function takes like names like the board, the L shape, the J shape, and just returns the color that they should be. And then finally, there's a little convenience function that maps a given number to the shape name. We could have avoided this, but I think it made the other function a little harder to read, so we didn't. At any rate, this is all basic, so let's go ahead and look at, see what it looks like in action. So this is, sorry, oops. Read that, Okay, so get rid of that. Oh my God, right? Like this is Tetris. We're done. It's obviously. Anyway, so this is what we have so far, and that's not so bad. Get back to my slides. I need that to stop happening. Okay, so we've got that L piece falling. We know what the next piece was going to be. Except the piece isn't falling, the game is static, it's not actually a game yet. So what we want to do is open up a WebSocket to the server, and then we're just going to have the server send us these two pieces of information. And then every time we get the new game state, we'll just call this draw function and constantly refresh that. So that's pretty simple. As a bonus, we're almost entirely done with the JavaScript now, and we can move on to Elixir, which makes me super happy. All right, so next we're going to introduce just a basic Phoenix channel. We're going to ultimately use this channel to send updates down, but for now it's just almost nothing. So here's a very basic Phoenix channel to support the game interactions, and basically, right, all it does is it lets you connect. And the channel's no good without a way to get to it, so we had a route to the router right there. And then in our JavaScript file, we go ahead and we connect to the socket when we load. Once we've successfully connected, we're going to log to the console just so we know, like, yeah, the connection worked. And so let's go ahead and do that and make sure that we can see it working in the browser. Yep, all right, so we got another channel. So things are looking good. Okay. So next we want to have the channel provide the mock data. So right now we've got mock data, it's hard-coded into JavaScript. Rather than hard-coding it into JavaScript, we're going to hard-code it into the Elixir side and just push it, right? So first off, we're just going to send any message at all to the client. So we want to push our message to the socket after we join the channel. Chris mentioned that they made changes. They added this handle info, and this is awesome. Chris, I like it. So basically, once somebody connects, we send ourselves an after join message. Then we handle that message and we push down that socket the Tetris state, which right now is this empty map that's sort of representing the state, and then that'll change in just a second. Anyway, I'm not going to show you anything here because there's not a whole lot to see. So the JavaScript is still rendering its own fake data at this point. So we're going to fix that. We're just going to move that data into the channel. So here's the channel, right? This is just the exact same data. I literally copied and pasted it, and then I put that little thing right there in front of it. Anyway, so yep. Now the JavaScript changes to use this. We get rid of the mock data, and inside of here, when we get the Tetris.state or the Tetris state event, we log the payload and then we just draw it. So using the same code before, we just plot it onto the canvas. So now the JavaScript is extra stupid. It doesn't know what to draw, and the Phoenix application tells it what to do. So this is like a nice foundation for where we're going. Next, we're going to add a separate process that we run to handle connecting this channel to the running game. So for now, it'll just be a separate process that sends this message to our connected WebSocket, and we'll build out from there. So here we spawn it. All we do is we spawn a new function. We spawn a new process running that function. And then over here's what we're actually running, right? So again, I've just moved this big chunk of static data over to a different module. This module will ultimately be responsible for rendering our game to the WebSocket, and it'll just send these messages repeatedly. So obviously, again, this is very basic refactoring. Let's go ahead and look at it. And for a little bit, all you're going to see is that I changed some code, and nothing is different except for, oh no, this time it's different. Oh, hold on, I have to refresh over here because I'm not even live coding. This is happening. Failed to start. I don't know why it failed to start. Try it one more time. If that fails, we'll just move on to the next commit, and everything will be fine. Yeah, no, there's a bug in this commit, guys. So, moving on. All right. So what we're going to do now is we're going to send that board to repeatedly to the WebSocket. So what's going to happen is that WebSocket process that we spawned, it's going to ask whatever the running game is, which doesn't exist yet. It's going to say, hey, what does your board look like? And then it's going to get back these 2 bits of data, and it's going to send that to the browser repeatedly, and then that's just going to call that draw function. So this is how we're doing it. We've set a render interval of 100 milliseconds, and then we send ourselves a take message on that interval. So this is the WebSocket process that we spawned, and it's just sending itself this message over and over and over again. And then we put it into a loop, and every time it receives the message, it pushes, cut it off, but this is that same data down the channel. And then it just loops again, right? And for good measure, we output the standard out so that it's clear this is actually being called. Since the render results are not going to change until later. So we will run it this time. It will totally work. There we go. Okay, so you can see it's been getting some data. And then, hey, look, it's the exact same thing over and over and over again. But if you look over here, you can see also, if I can run it again and connect. Oopsie, oh, I don't even know what that was. No. 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 Okay. Sorry about that. Anyway, we look over here and we can see it's ticking. Okay. So, still looks pretty much like it did in commit 2, but we're pushing the implementation details out further. Okay, so enough of the fake stuff. We ultimately want to have an actual game process running. So what we're going to do is we're going to fake a game process. So for now, when someone joins the channel, we're going to spin up a new Tetris game. And we're going to pass that game into the WebSocket process we spawned. So we have a game running over here. We have the WebSocket process that's talking to the browser over here. And that WebSocket process can ask the game, hey, what do you look like? Over and over and over again. So easy enough, we start a game, we pass it into the WebSocket.run function. Okay, so the Tetris game module is just one more place to shove this hard-coded game state down. So my process here, if you haven't caught on yet, is to gradually push state lower and lower and lower until it finds itself a nice little GenServer where it's going to change over time. So let's see how the WebSocket process changes now. And it's pretty basic, right? The only difference from what you saw before is we're calling Tetris.game.getState, and we're passing it the game that we're handed. Right now, this isn't even anything useful, because if you look, it doesn't care what bits, right? It always renders this board, but this gives us a shim to begin to look like a GenServer. Okay. So yeah, this module has a very small responsibility. All it does is get the state and hand it to the website. So nothing changed from the end user's point of view. I'm not going to go ahead and run it this time. I'm supposed to, but whatever. Next, we're going to introduce a struct to hold the game state. So this is where rather than just having hard-coded data about what the board looks like, we start to have this logical concept of what is a game of Tetris. So we introduce a struct. Right now, it's very sparse still, and we return that state. We return that from the start function. So now we're returning a Tetris game state struct, and then here get state is actually extracting some data off the struct and turning it into this for the end client. This is actually a bad design. This should happen in the WebSocket, but that's not what I did. So we're going to deal with it. Anyway, and like I mentioned, this still it's not a separately running process or anything, but I've modeled it so that it kind of looks like one, right? So you call start on it, you get back a two-tuple that has OK and then like something, and then you pass that thing into the getState function, and you get data out of it. So if this were a PID rather than a struct, the end user wouldn't care. So we're not going to have to change our usage of this module, and that's just a nice thing to do when you're refactoring. Okay, so the next thing we're going to do is we're finally actually going to change the game to be a GenServer. So like I mentioned, from the context of the calling code, the public API is still just start and get state, but this is actually a GenServer now. And so when we handle a call, get state, we pull the board and the next off of the state. The state is our struct right there. And we reply, we give this as our response to the get state call, but we don't change anything. We keep our state the same. Anyway, like I said, it's nice that we can move from this thing that wasn't a process to this thing that's backed by a process. And the caller doesn't care if we're using concurrency to give them what they're asking for or not. So now we're going to introduce a module that's going to know about all of the Tetris shapes. So we finally get to the point where we're actually doing Tetris-y things, I think. So we don't want to specify the pixel array for the next piece in what the concept of the running game. We just want to say like there's an L coming up. So we modify our game state to use an atom for the value of next. And then when we send the state for rendering, we get the pixel array for what that shape would be at the 0 rotation. And so that comes from the shapes module. And so let's look at the shapes module. Again, it's a stupid refactoring, right? We pretend that we know how to get all these shapes and rotations, right? But again, we're just hard coding the data for now. And this is just it's hard to keep things in your head, right? So it's very easy for me to just like make really stupid refactorings and just push little bitty things further down the stack until I actually have something. So I'm going to go ahead and run it. It's still not going to look any different, but it's doing more to look the same, right? So that's a thing. All right, y'all ready for this? Oh yeah, that's right. That's what refactoring is supposed to look like. So anyway, so next we need to fill out the shapes module so that it's not that stupid thing that's only knows how to talk about one shape. And we need to start overlaying our current piece on the board. So right now the board includes like the concept of the currently falling piece. It's just like slapped into that pixel array that we're giving back. That has to go away because it's got to move. Anyway, so forgive the formatting of the slide here, but hey, I can fit it all in this way. So this is really stupid. I'm using module attributes to just like lay out. It's very clear that these are the Tetris shapes, right? So there's a J, there's an S. They just look like Tetris shapes. And then I've got this rotate function that we're importing from the Tetris rotator. And it's a pretty stupid thing also that just knows how to, given some pixel array, how to rotate it in 90-degree increments. And that's so that we can, at compile time, generate this map that just says, like, here are all 4 possible rotations of all of the shapes that you'll ever have to worry about. Because we don't want to be, like, doing this at runtime. It's the same freaking thing every time. Anyway. And then here's the rest of the module. We've got a way to get a given shape at a given rotation at runtime. We've got a way to get the width or the height of a given shape and rotation. Really trivial stuff. We've got some mappings between names and numbers. So, earlier we had an L and it consisted of ones. So this one actually says like draw a yellow pixel. So this way we can kind of keep track of what's what going either way. And that's really all this is. And we also have a way to get a random shape. And so that's the whole of this module. None of this is terribly difficult, but there you've seen it all. And then here's the rotator module. Again, this is nothing particularly fancy. We've got basically this kind of funky little nested pair of 4 comprehensions that sort of traverses one way across one dimension of the array and the other way across the other dimension of the array. And that turns into a 90-degree rotation. Like it's I don't know that it's easy to see here, but trust me. And then all our other, like rotating by 180 degrees, just consists of calling rotate by 90 twice, right? So this is easy. And then if you try to rotate by something else, I throw an error or something. And then we've updated the game state to include a few more values. So previously we just had board and next. Now it also includes the current piece. The current piece is rotation, its x and its y coordinate. And then we have a way to get the cells for the shape. So this is just a way to say, like, what are the coordinates on the board where the shape presently overlaps the board. And it returns a list of 2-element tuples for the x and y coordinates. So now in our game, we fill out the state a little bit more. So now you can see we've got the board, it's empty when you start off. The next piece is an L, the current piece is an L. Our current rotation is 0. It's at 5 and 0 for its x and y coordinates respectively. And then we call this function now. So this is the only other thing that's changed is when we send our state to the caller, we just overlay the shape onto the board at the position it's supposed to go. And obviously we don't actually change our board when we do that because that's not what happens. And so here's how we switch the current piece onto the board. So basically we iterate over the board in a couple 4 comprehensions, and then if the current position, if the current position in the scan that we're in contains part of the shape, we push that part of the state's number, that part of the shape's number onto the board. So that's really it. And so we can see this in action. And this is where we can actually start to see it look like a Tetris game, which I think is important when you're building a Tetris game. So to start with, it is not going to look different, but we'll fix it this time. Okay, so it's the same thing. But then if we go back here, let's just come in here and then the Tetris game. And we will say, hey, our current state, our current piece is like an S. And I don't know, it's further down the board. Oops. And now, holy crap, guys, like, it's different. It's really easy to get claps, this is awesome. Okay, so we're like 44 slides in, and this is kind of the halfway point, and it's starting to look like a game, so that's nice. So now we're going to make the piece fall down every tick of the game clock. So this is a component of Tetris, right? The piece falls. So we do this again by using Erlang's timer module to send ourselves a tick message every half hour, twice a second. And then we handle that with the handle info function head. So we're just sending our GenServer the message tick. And then every time it gets the message tick, it's going to increment the state y component by 1. So, and then actually update the state. So that's easy enough to do. Also, in this commit, I fixed an off by 1 error in the JavaScript, but we're not going to talk about that. Oopsie. So if I did it right, yeah, we have a piece falling. So this is basically Tetris. Of course, it's going to keep falling and falling and falling. Right? we haven't done that part yet. Anyway, so now we're going to add keyboard interaction. So we're going to modify our game GenServer. It's going to support a handle input cast now. So it's just got this public API for handle input. and you give it an input, and this is just an arrow. And then what it does is it's not a reply, right? It's a cast, and then it modifies its state by returning whatever the interaction handle input function returns. So let's look at this interaction module we're talking about. So here we've got an interaction module. It has a handle input function, and the first thing it does is just defers to this other function called do handle input. This is important later, but for now it's superfluous. And then we handle two events, right? We handle move right and move left. Does anybody see the bug that I introduced in this commit? Right. Those aren't different. Those should be different. Okay. So that's all right. Anyway, so if you ask it to handle any event it doesn't know about, it just doesn't change anything, right? It returns the state that you passed it. If you give it an event it knows about, it updates the state, or returns a new state rather. So now we need to look at how to support inbound events on the channel. And so in order to send input into the game, we need the PID for the GenServer. So here we're starting the game. And then down here we're actually assigning to the socket. This is a neat thing you can do with sockets. We're assigning to the socket's game key the PID. So then later, when we have an event, we can fetch what the PID is off of the socket. And then we can send the input in. So, sorry, I actually pointed that out in the slides and everything. Anyway, so here we're just allowing the JavaScript, the JavaScript application to send in a JavaScript object that maps an event to an event name, and we pass the event name into handle input. And we actually convert it into an atom. Don't do that, because that's a big old DDoS. Somebody will use all your memory. But it's really convenient if you're giving a talk. Okay, so once we've joined the channel, we're going to bind the Windows key up event, and this is JavaScript again if you didn't recoil. So presently, no matter what you push, we're just going to push the move right event to the channel. And so let's go ahead and have a look at it. Okay, so that's sadly it moves off screen pretty quickly, but we have keyboard handling, right? So that's nice. It's getting ever closer to becoming a game. So now we're going to introduce moving left. That's a big feature, as well as introduce a pattern for mapping our browser actions and game actions. So first off, choosing the direction you can move. So here's the JavaScript again. It's just another case statement, right? We pass the JavaScript event in, and we get some string out, and that's the action that we're going to send. It's simple stuff, and I also fixed my little snafu in the interaction module, so it's not always moving right. So if we try this one out, we can move both directions. All right, okay. So now we need to be able to rotate the piece. So we're going to allow the up arrow to rotate the piece. And so here's the interaction module change, right? We just added a new clause for rotate clockwise. And all that it does is it, modulo 4 increases the rotation of the state. And here's the JavaScript. Again, very trivial at this point. Of course, we can see in action. Bam! All right, so it's ever closer. Of course, we still have no boundaries implemented, so I can do this, and I can do this, and we can fall off the edge. But let's go ahead and at least keep it from going past the board edge. So now you can see why we deferred the do handle input thing from handle input. So basically what we're doing here is we're getting what the new state would be after handling the input. And then if the new state would yield some invalid state, we just don't return it, right? We return the original state because, hey, look, validation checking. And so that makes it pretty easy to just start defining what a valid state is, right? So if x is less than 0, it's not valid. If this thing's past the right side of the board, it's not valid. Past the right side of the board just means, hey, look, if the width of the current shape plus the current x is greater than or equal to 11, because we know the board is 10 wide. Anyway, so now we should be able to move past the board edges, either place, either right or left. So let's look at it. And you have to trust me that I'm actually trying, right? I could be faking this, but and it works no matter how we rotate it, so that's nice. Of course, again, we're still falling past the edge. So now we want it to actually, when it hits the bottom of the board, just stick, right? So what does it mean to stick, right? It just means we're going to permanently smoosh that piece wherever it was. So here we're going to introduce a function to handle this slightly increased bit of game logic. Nothing still very complicated in this at all. So if there's a collision with the bottom of the board, we update the board to include the overlaid shape. And then we pull the next shape onto the current shape. We set x and y to 5 and 0. There's a bug here. I should also set the rotation to 0. I don't. And then we update next to be a random shape. Otherwise, we just drop like we did before. So this happens at the point that the piece would be dropping. And then collision with the bottom looks very much like collision with the sides did, right? If the height plus the y is greater than 19. Anyway, there's also a bug in the JavaScript, which I fixed so you won't get to see it. But if you remember, we were, if the position was 0 on the board, we just did nothing in the JavaScript. So this meant that we didn't clear it. So like the piece would just like smush at various places. Sorry, that's actually on the next piece. When we were drawing the next piece, when the next piece updated, you would still have the previous piece showing as well, and they'd just kind of be blended. Anyway, so that's not terribly important to tell you. So let's see it actually hit the bottom of the board. Okay. Most of the talk, by the way, is just watching this L fall. Whoa! Yeah. Of course, there are issues. So, for instance, it doesn't care that it just fell through the other piece. Yeah. So anyway. So next, we're going to handle collision with other board pieces when falling. So we're just going to add a check to see if the next step would yield a collision with a non-zero cell on the board. If it doesn't yield a collision, we take the next step, right? We increment y. If it does, we do what we were doing for the collision with the bottom. We just switch the shape onto the board. And then to see if there's a collision with the board, we just say, do any of the next coordinates intersect with the, does the cell at any of the next coordinates contain something other than 0? So that's that. And then this cell add function is very simple, but I want to show it for completeness. So you pass the state and an xy tuple, and it'll just return whatever was there. So let's go ahead and look at this commit. So now, and while this is falling, I'm going to get some orange juice. And now we're going to have a collision. And it should stop falling when it's that piece. Awesome. Okay. Now, one thing we don't do, didn't want to do this yet. I want to show you one case we don't handle yet. So, it only actually handles collision when it's falling, so I can be like, boop, and that's not, we're still not at Tetris. So let's go ahead and handle that bug. So here's that change. It looks a whole lot like the tick change. It's slightly simpler because previously, on the tick change, we had to say, what's it going to look like, whereas here we just defined that it would be invalid, right? If there was a collision with the board, then it would be a valid state. But this is essentially the same thing. And so now we can't do that anymore. And how am I on time? I'm going to skip showing you guys this. You can imagine that we weren't able to do that. All right, so we were hard coding the next and the current shape previously, so we're going to stop doing that. So, one second. Let's prepare for this. Okay. So here we're calling shapes.random to get random shapes for our game. So previously these both said L, now they're just called as shapes.random. This is obviously important. What's not so obvious, like if you come from another language and you you can like call random and you get random values because that's what you want. Before you call random, you have to seed the random number generator, and you have to do that in the process that's making the calls to the random module. So here in our struct function, we call random.seed, and then down here, everything should be good, right? It's seeded. So let's see it in action. So let's go ahead and start a new game. Oh, didn't run apparently. Oh, sorry. Alright, so cool. These aren't both L again. So let's just refresh it and see those random pieces. Those random pieces. Right, so remember when I said that you had to seed it in the process? This is not that process. This is the public API. So this I made this mistake originally when I did this, long ago when I first wrote this. So we seeded the random number generator in, and when you seed the random number generator in Erlang's random module, it puts the seed in, and it increments the seed in the process dictionary. So the process dictionary is obviously, as you might guess, process specific. So the fact that we seeded the RNG in that process doesn't do anything in the new process that we spawn, right? So anyway, so that's not going to work. We'll fix it, and we fix it by we move that call to seed down into init, right? So that's the public API. This is actually happening in the process. So this is a thing to just think about when you're doing GenServers. And so that was easy, and we'll go ahead and see it actually do randomization. There we go. Hey, look, they're different pieces. That's nice. All right. So the next thing to do, really, we're colliding with pieces, we're colliding with the edge, we're sticking when we hit the bottom, but we want to clear lines when we take the game, right? If we filled out an empty line or a full line here, like we got our Tetris, nothing happens. The line sticks around. So we're going to delegate to a function on the state module that knows how to clear lines. So right here, when we we get our board with overlaid shape, then we're going to go ahead and clear lines, and we'll get back a state that would have the clearing applied to it. And then we're going to use that for our new state rather than just the overlaid shape state. Anyway, so let's go ahead and look at what that clear lines function looks like. So this sucker's got some meat to it a little bit. So first off, we have our one-arity public function. So you pass in a state, you get back the same state, but the board has been updated to include whatever clear lines this three-arity function returns. And this is got a couple of little accumulators that you pass in to start out as empty lists. And anyway, this is just a recursive function. It iterates through the lines on the board. So it grabs the first line on the board. If it's clearable, then it accumulates that line over to the cleared accumulator. If it was not clearable, then it puts it back in, sort of the board accumulator. And then once we're done, we'll have a board, like, if we cleared 4 lines, we'll have a board that has 4 too few lines, right? And so then we shove 4 empty lines at the top of the board, and then that's it. So that's all that clearing the board looked like. So this is 9. Okay, so let's clear a line. This is going to take some time, people, because this thing falls a little bit too slowly. But it also gives me a chance to drink orange juice. So, how much fun is watching somebody play a really slow game of Tetris? I'm curious. That wasn't even a good place to put that. Also, the browser is now too little, so I'm getting movement. See, I guess we're going to clear that second line, huh? We've got to test it. We're getting closer. That was a dumb place to put that too. How's everybody doing? This is going good? Oh, come on. I should have seeded the random number generator with something I knew. Hey, look, how almost done with this line. Let's just go with it. This will tell you what we're doing now. No, we're good. I'm just going to clear this line. This is a lot more fun than I thought it would be. It's like I get to troll a whole lot of people at once. Okay, are we happy? Is this good? Let's go ahead and scroll down then. I'm so glad that we're all right, so back to this. If we wanted to actually get the the score, we're not scoring in this implementation of Tetris, but if you wanted to, this would be the place that you would return like how many lines were in the cleared bit over here, and then the thing they call clear line would use that to update the score. But anyway, we're not doing that. Yeah, so that's it for getting Tetris working. At this point, anybody, let me verify that this is my public IP. 1 second, because I meant to do that before I started talking. So where are we at? Hold on.
Right there.
Okay, so it's .8.100. Let me make sure that's anybody that wants to take that IP down, and I'm just going to fix it. Whatever. This is .8.100. So ignore that. Put a 100 there. So people, I'm going to need help. Anybody with a laptop, connect to this, and I'll get it running so that you can at least play your one-player game of Tetris instead of paying attention. Sorry, it's .100. This part is a lie. And it's port 4000. So while everyone's doing that, it's been bothering me. The next piece has always been drawn in the same color rather than the actual color of the piece. This is easy to solve. So we're going to multiply each cell in the next 2D list by the number that corresponds to that shape. So basically, previously we just returned this shapes.get, right? Now we're going to pipe that into this colorize function, and it takes the next piece's name, and it gets the number for that name, and it multiplies it by whatever was in that column. And that column is either 0 or 1, so this just works, and it gets us to the number, to the color that we want to be. And so this should be looking pretty much done with that change. This is 0C77. Is anybody on there yet?
The AP is filtering traffic between people. Ask me how I know, because it's part of my demo.
Oh no, how do you know? Just kidding. So is really nobody else can play it? This is going to be miserable. I suppose I should have checked that. I just didn't consider it. We can show it as collaborative still, but this is pretty unpleasant, to be honest. Anyway, so one thing that we can at least show, right, this is using the red color for the next piece now. And it's not collaborative yet. That's the next little piece to show, although apparently I can't actually have anyone play it, which is miserable.
Well, in your port 4000, maybe they're trying...
No, it's all traffic between anyone connected to the AP. They filter for security reasons.
I should have brought a router.
I thought about buying one.
Yeah.
For my demo.
Huh? That guy's smart. Hold on. We can do this, people. We have technology. Change my hotspot password real quick. All right, so the new password is ElixirConf. And I'm going to turn it on. You're going to see a hotspot available called K-Droid. It's K-E-H Droid, and I've got to switch to it. How am I doing on time? I've got 10 minutes, right? I have 1 minute? I thought I had 10 minutes. This is no good. All right, so let me get my IP address real quick. We can do this, people. Anybody able to connect?
What is the IP?
The IP address is up here. Nope, right here. Is it not on? No, it didn't connect. Hold on a second. So close. My laptop's not going to connect. Oh, that's interesting. There's no escaping the demo gods. I will at least show you what the collaborative bit is, and this is super super frustrating because I was really excited about getting people to play Tetris together. Okay, so let's come back up here. So the only piece left to do is to make the game collaborative. So right now, every time someone joins, it starts up a new GenServer, right? And then the WebSocket renderer gets that GenServer passed into it. Instead, what we're going to do is when we start, we're going to add these two functions to the main Tetris module. So we start a game when we start it, and I'll start a game. Oh, hold on now, this may work. All right, so, oh, it's not connecting because it thinks it knows the password. And then you can fix that next time that comes up. Hold on, I can fix this. Okay, so ElixirConf. Okay, so we basically start the game, we register the process, and then we have this restart game function. And so hold on, I can give you an IP address now. All right, so my IP address is right there. So it's 192.168.43.184, and it'll be running on port 4000. So 192.168.43.184. People are connecting, awesome. Okay, so I'm going to kill it though, because I've got to check out this commit. Okay, this is fine. Okay, so now we have a collaborative game of Tetris, and I'll show you what the last little change is while everybody connects and plays with each other. Oopsie. Okay, so this is the only other change that we have to make. Right? Ah, come on. So basically, instead of using the new game that we created, we just pass in the Atom game, which is that registered atom, that registered process. And so now everybody's eventually going to the same game. Is it working? Is it horrible to play because you're all fighting each other? That's amazing. Okay, so this is, I don't know how many of you are doing it, but right? So I thought this would be a lot of fun, and yeah. It's this is good stuff. So, so I guess I'm out of time. Let me go ahead and at least sort of show my final slide. Right. So here it is again. This is the repo. This is Elixir Sibs again. I'd love new subscribers because it buys my children food. Look at that, using pity. And then iStillBlood.com. That also buys my children food. They get along. Anyway, so that's it. And thanks. I don't know that I have time for questions, but we'll see.
Let's take one question. Yeah.
Okay. Well, we take questions while the other guys are getting set up.
That's good.
All right. Menorans can come on down.
How do you define collaborative?
I don't know. That's up to you guys. Or you folks.
Let's get Josh to begin.
Yeah.